Welcome to this new episode of Not So Fast. In this video, what we are going to discuss is the fundamental theorem of calculus, and in particular, when not to use it. So let's have a look at a quick example where on the left you've got the integral from -2 to +1 of 1 over x dx. Now for people who have practiced a lot integral solving, then what they are going to do is basically look for whether or not they know the antiderivative of the integrand. If they actually do, they are going to directly charge into the problem without thinking twice. Now, as a result, because they know the antiderivative is log of x, they are going to do the following manipulation. They are going to put it in square bracket like this, and then this is going to be equal to the log of 1 minus the log of the absolute value of -2, which as a result is going to give minus log of 2. Now it turns out that, as in any case where we tend to jump into a problem without thinking too much, then it turns out that it can sometimes go wrong, like this. And what we are going to do here is try to understand why. So we've seen so far that there seemed to be a problem in the typical reasoning that we have presented just before for the integral we looked at. First of all, before understanding where things went wrong, we will try to understand what the trained person actually tried to do in the first place. It turns out that the reasoning that we have seen before is based on something called the Fundamental Theorem of Calculus. It reads as follows: the integral over the interval ab of f of x dx is equal to uppercase f of b minus uppercase f of a. Now, what are these things and what do they mean? Well, the left-hand side actually means that this is the area that is between the graph of f of x, which is a continuous graph of f of x, and the x-axis. Okay, so that's the meaning of the left-hand side. And the right-hand side is a totally different object. It's actually relating to the antiderivatives, which are local operations, at the two endpoints, a and b, of the interval being considered. And so you see here that there is something very specific where we see that there is two different objects that turn out to be equal to each other when some conditions are met. In particular here, the condition is that the graph is being continuous. Now, the notation for antidifferentiation that I've used might be probably new to some of you, but I think it's quite striking, that it shows that somehow we are doing the inverse operation of a derivative. Now, this is not something of my invention. If people are interested, this is a kind of notation that can be found when people do so-called fractional calculus. So people who are interested might want to have a go at it. Now, let's go back then to understand what went wrong before. So we had that the integral from -2 to +1 of 1 over x dx was minus log of 2. Now the issue, if I interpret this in terms of graphical representation, that the left-hand side actually looks like this. Now, one of the problems is that you see that the graph of f of x actually diverges when it tends to 0, both 0 from the positive x and 0 from the negative ones. And so as a result, the actual graph of f of x is discontinuous at x equals 0. Now, what this means that this is discontinuous at x equals 0 means that somehow I'm trying to determine the area under a graph which is basically punctured, okay, at a given point. And because it's punctured, obviously I can't, define the area that is below that curve. So as a result, when it comes to the initial integral that we've defined, it turns out that this integral is actually meaningless. The corresponding object actually doesn't exist. So what do we do then? We've got this object that doesn't exist, that seems to be equal to minus log of 2. So what does that mean? And in fact, can we actually try to make sense of this? There is actually a way to try to make sense of this. This way relies on the fact that we can look separately at the interval from -2 to some value minus a, which is not 0. And because here you see that the graph is continuous on this portion, then we can use no problem the fundamental theorem of calculus. Likewise, this part here is actually well defined because the graph of f is actually continuous there. As a result, we can try actually to add up these two areas, so that's going to look like this, and then try to see what happens when we take the limit when a tends to 0. And this is well defined, and this will enable us to avoid trying to determine an area under a curve with a puncture. So this particular strategy to make sense of integrals with graphs that have like punctures in them is what is called Cauchy's principal value. Now the way they are denoted is like this: PV of the integral from -2 to +1 of 1 over x dx. Now it turns out that because the fundamental theorem of calculus actually holds for the individual sections, so from -2 to -a and then from +a to +1, we can use the same strategy that we had used before. So we would get something like this. For people who know how to solve such integrals, we'll get the log of absolute value of -a minus log of 2 and then plus log of 1 minus log of a. Now you see that what happens is that these two logs disappear, they compensate each other. So essentially, they overshoot to infinity in one direction, but then to -infinity in the other. And these two contributions actually compensate to give rise to a finite value. It turns out that this final value is the very same minus log of 2 we got in the first place in our example. The big difference, though, is that in this particular situation, the left-hand side actually exists. It makes sense and it's well defined. So the whole strategy and scenario is actually fundamental theorem of calculus approved, and it's totally valid. Right, so what do we take home from this particular example? Well, the first message is that we should try to make sure that the left-hand side and the right-hand side both are well defined when we want to apply the fundamental theorem of calculus. In the case that we have looked at, there was a way to interpret the left-hand side in a consistent manner with the right-hand side, which was this Cauchy's principal value strategy. Now it turns out that this strategy is very far from being useful in all situations. So for example, if instead of 1 over x, you take the integral from -2 to +1 of 1 over x squared, then the object itself still doesn't exist. But on top of this, the fix that we used, which was Cauchy's principal value, doesn't apply either. So what I mean by that is that there is no compensation that we've seen earlier in the case of 1 over x. So essentially, the whole integral blows up and basically is infinite. So we see here that there is basically some care that needs to be put when addressing any problem when it comes to integration, and in particular, try to figure out whether your use of the fundamental theorem of calculus is actually legitimate.